Okay, like I said, these first few days we're just going to be going over things that you hopefully already know about. The last lesson we talked about forces. We reviewed what net force was and what a few of our main forces look like. Today I'd like to review with you the idea of mass and density. So I want to remind you of the role that mass plays. We talked about how forces make things speed up, slow down, or change direction. Well, the other thing that has a role in how quickly this happens is mass. The more massive the object, the harder it's going to be to speed up, the more gradually it will slow down, and the harder it will be to get it to change direction. So mass inhibits acceleration. It doesn't stop it, it just slows it down. So the greater your mass, the lesser the rate of acceleration. Mass is sometimes called inertia. I don't know if we ever used this word last year, but it's a word you should know. It's a word that you will see used all the time in popular culture. And inertia just means your tendency to keep doing what you are already doing. And mass tells the object's propensity not to want to change. So if an object's in motion, we know it wants to stay in motion. The more massive it is, the harder it's going to be to stop it from doing what it was originally doing. If the object was at rest, it's going to want to stay at rest. And if it's going in a straight line, it wants to continue moving straight. The amount of inertia, i.e. the mass, they're synonyms, tells how hard it's going to be to change it from its state of motion. So what actually is mass? When we look at an object like this and we know it's got a lot of mass, in fact 2 kilograms worth of mass, what are we talking about? Well, mass is actually a measure of the amount of matter that is contained in that object. And by matter, we're talking about things like protons, neutrons, and electrons. So the more matter, the greater the mass. Right alongside of mass is the idea of density. How dense is the object? Well, hopefully you remember that density tells you the amount of matter in a given volume. So every material has a different density. So this is aluminum, this is lead. These have the exact same amount of mass. It just so happens with the lead, the mass is packed together tighter than it is with the aluminum. This is copper and iron, and they also have the exact same mass as this aluminum. All of these have the same mass, but in one, the matter, the protons, neutrons, electrons, are packed together more tightly. Okay? So that is density. Concentration of matter in an object. You find the density. This is the symbol. I don't know if we've used this symbol before. For this, I know we used it when we were talking about the resistance of a wire. But this is the density. Rho is the Greek letter. And you find it by doing mass over volume. Hopefully remember all your volume formulas for different shapes. And you just get the mass, the dimensions, and you're able to figure out the density. Density is really important because it lets us identify the material. So this aluminum and this aluminum are totally different in terms of their size and mass, but the ratio of mass to size will be constant. All pure aluminum will have the same density at the same temperature. Okay? So every material, whether it's copper, aluminum, iron, lead, whatever, has a unique density. The way you measure density in terms of units, mass over volume, the standard should be kilograms per cubic meter. I want to remind you what a cubic meter looks like. This thing in the back of my room, you've seen it before, is a cubic meter. It's a meter wide, a meter deep, and a meter tall. The amount of space inside of that, and there's a lot, is a cubic meter. You'll see inside I hung a 1 liter bottle. You guys are real familiar with 2 liter bottles, but that's a 1 liter bottle. And 1,000 of them will fit inside a cubic meter. So a cubic meter is a lot of space. And when we're dealing with density, density is the kilograms per cubic meter, and that is the standard unit for density. It's not the most common unit of density you'll see out there. A lot of times, especially when you're dealing with small quantities, will be measured in grams per cubic centimeter, or even more common, grams per milliliter. So be ready to see a bunch of different units, but you always want to work standard, okay, when you're dealing with other equations, and that is kilograms per cubic meter. You have a density sheet. If you don't have it from last year, that's okay. Whenever you need it, I will post it until we're back in person and you can get another copy. But these are the densities of different materials. Again, all values are in kilograms per cubic meter. That's the standard. If you want to work in a different unit like kilograms per liter, grams per milliliter, or grams per cubic centimeter, just divide these by 1,000. So you'll notice pure water, distilled water, is 1,000. That's kilograms per cubic meter. If you want it in grams per milliliter, it's just 1. So again, if you take a look at our cubic meter, if we filled that with water, that would have 1,000 kilograms of water inside of it, which is around a ton. In fact, that's the very definition of a metric ton. Okay? So again, all your different densities. The final term I'd like to teach you is the term specific gravity. This is a term that used to be used a lot. It's still used pretty frequently, so I would like you to know what it means. And specific gravity just refers to the ratio of an object's density compared to water. So the nice thing is specific gravity doesn't have any units. You can work in any unit you want. So this has a specific gravity of 2.7. That means it's 2.7 times the density of pure water. So if I was working in grams per milliliter, I multiply 1 by 2.7 and I get a density of 2.7 grams per milliliter. If I was working in kilograms per cubic meter, I would multiply again the 1,000 for pure water by 2.7 and I get 2,700. You'll notice this sign that I saw in Princeton. They give the specific gravities of these different chemical reagents. And you'll notice it says specific gravity somewhat bigger than 1.26. A specific gravity somewhat bigger than 1.23. Again, no units. Specific gravity doesn't have units. But then they also tell you that it does have a weight of 10.3 pounds per gallon. That is also a unusual, but I guess at least sometimes used, unit for density. Okay? Pounds per gallon. Again, we will never use that. Anyway, that is all I wanted to tell you about mass and density. You have a few problems online just to show me that you understood this. Please get them done by 4 p.m. Thank you.